Hello everyone. Last time we defined rings. Whenever a new mathematical object is introduced, a natural question follows. What can we deduce from the axioms alone? Today we'll examine four simple identities that hold in every ring. They are so familiar that one might be tempted to take them for granted, yet the definition of a ring never explicitly tells us that multiplying by 0 gives 0, or that the product of two negatives is positive. These facts emerge from the axioms themselves, and this is one of the pleasures of the algebra. Small collections of assumptions already contains much more information than is visible at first glance. Let us see how these identities arise. I denote the start of the proof as this triangle here. Now, let's start with the first one. Let's show that 0 times a is equal to 0. So 0 times a is equal to 0 plus 0 times a. It's because 0 is equal to 0 plus 0, right? And here by distributivity law, we have 0 times a plus 0 times a. Now this follows because of distributivity. So in the end, we got 0 times a is equal to 0 times a plus 0 times a. Now from this point on, we can add the additive inverse of 0 times a to both sides, and we'll get 0 is equal to 0 times a. Now here keep in mind that R is a ring, which means that R and plus is an abelian group, so we can cancel terms additively. So each element of this ring has an additive inverse, and we can add them to both sides. Okay, for this one though, let me mention this explicitly. Okay, I'll write it as plus minus 0 times a, right? Remember, we denoted the additive inverse of element by minus that element is equal to 0 times a plus 0 times a plus minus 0 times a. Okay, and from here we get that 0 is equal to 0 times a, because the element and its additive inverse, they give 0 by definition, by the axioms we provided in the rings. Alright, so we've settled that 0 is equal to 0 times a, and if we show that a times 0 is equal to 0 as well, then we are done, right? Because it will also mean that a times 0 is equal to 0 times a. Now here let me mention that we got 0 times a is equal to 0. Okay, now the similar procedure is for the a times 0 is equal to 0, so I'll try to be a little bit concise here. But we have a times 0 is equal to a times 0 plus 0. Again, we use the distributivity, 0 plus a times 0. Also remember that we agreed that we are denoting this with multiplication as AB. Alright, then again by cancellation we have 0 is equal to a times 0, right? So basically a times 0 is 0 as well, which means that 0 times a is equal to a times 0, and they are both equal to 0. Okay, the first one is done here, so let's move to the second one, and the second fact states that minus a times b is equal to a times minus b, and it's equal to minus ab. Now let's prove one by one. First we have that minus a times b is equal to minus ab, okay? Alright, so here we have, let me write this clearly for the first time. Since a plus minus a is equal to 0 by the axioms of the ring, we have ab plus minus a times b is equal to, now you might ask why I take this sum. It's because I want to show that minus ab is minus a times b, and showing that minus a times b is the inverse of ab will be enough, because by definition then we might write that minus ab is equal to minus a times b. But if we get that their addition is 0, it will already imply that this is an additive inverse of this one. So we will be done there. Nevertheless, let me continue, and by writing down you might understand it better. So here we have, again, by distributivity, we use this all the time. I will not mention this every time I use it. A plus minus A times B, right? And since this is 0 by axiom, 0 times B, but 0 times B is also 0 because we proved this in the last step. We proved that 0 times A is equal to A times 0 is equal to 0. So here we have 0 as well. Now, as I said, we showed that their sum is 0, which means that this element is the additive inverse of this one. Let me, for this time, write this down, and I'll skip it for the next time. So minus A times B is an element which, when, let's formulate this as such, added to AB gives 0. Therefore, it is the additive inverse of AB. Hence, minus A times B is by definition minus AB, since additive inverse of AB is minus AB. We denoted it earlier. Now let's prove that, what was there? A times minus B is minus AB as well, and then we'll also have that these two are equal to each other, of course. Alright, the second one is done in the similar way. A times minus B is equal to minus AB. I will not be writing details that much as I did in the previous part because they are very similar, and I would rather save your concentration on the next ones. Yet here it is. As I said, we do this in a similar way. Let's write this as, like, our main aim is to show that its inverse, like inverse of AB, is this one. So let's write this down. AB plus A times minus B. By distributivity, it's A times B plus minus B. But B plus minus B is equal to 0 by definition, because minus B we consider as the additive inverse of B. So we have A times 0 here, which is 0, again by the previous fact. So let me write this here in fact, as this is done by fact 1. The same is applicable here, of course. Now, again we showed that, like, therefore A times minus B is minus A times B. Like, A times minus B is also additive inverse of AB. Now, we are done here because we showed that this is equal to minus A times B, this is equal to minus A times B, so they are equal, and they are equal to minus A times B. I don't want to rewrite this one more time. Writing these are enough. Now let's move into the third fact. We have that minus A times minus B is equal to AB. Okay, let's write this down. Third, minus A times minus B is equal to A times B. Now here I will want your concentration a little bit, because we can use the part 2 for this. Just look carefully. Minus A times minus B is actually minus A times minus B, right? Here we just used B as an element, like take this as some element x and this as minus A. Then minus A times x will be minus A times x, right? But instead of x, just plug in minus B. So here is what we did. We used the part B for that, part 2, sorry. Like, we established these facts already. Now we can apply them, and we can write minus A times minus B as minus A times minus B, where, like, consider this as some other elements, so that it's clear for you to grasp the logic. Alright, once we wrote this as such, we can also apply the fact 2 one more time and write this as minus, what it will be, minus AB. Okay, I hope it's clear. Like, let me write this by part 2, again by 2. Okay, so minus a times minus b is actually this by 2, if we take minus b as an element. And then we apply the fact 2 one more time to get that this one here is equal to minus times AB. We used the fact 2 straightforwardly. It is as it was in the fact 2. Now here this is equal to AB. And this is because, let me write the star here. And star stands for the following fact. In additive group, which R is, the inverse of the inverse is the original element. So minus times AB is nothing more than AB. Okay, that's why our identity here holds as well. So the most important part here was to show that this is equal to this one, and after this we can simply write AB because R is an additive group. Okay, now the last one remains, I believe. The last one is that if R has an identity, then it's unique and this identity holds. So let's write this down, the fourth and the last one. First, let's prove that identity is unique. One is unique. We'll use the simple procedure to prove that. It's to assume that it's not unique and arrive to a contradiction. Now, suppose 1 and say E are both multiplicative identities R. We usually denote identity as 1, but now that we suppose that there might be 2 of them, let's say that one of them is 1 and the other one is E, are both multiplicative identities in R. Now, since let me write this as such. Since 1 is an identity, 1 times E must be equal to E. But since E is also identity, E is an identity, 1 times E must be 1, right? Therefore, E is equal to 1, so the identity is unique. Or, like I said first of all, that we can arrive to contradiction, or you might suppose that they are both identities, but one is not equal to E, that they are different identities. And then you, again, follow the same procedure, you are showing this, and then we arrive at the fact that E is equal to 1, but since we assume that 1 is not equal to E, we arrive at contradiction, so the identity must be unique. These are basically the same facts. I went in this way, you might show this in another way that I described. And in fact, let me write this, or one is not equal to E and arrive at contradiction in the end. Okay, I think this is fine. And the last thing to show is this identity, right? Minus A is equal to minus 1 times A. So minus A is equal to minus 1 times A. Now again, we follow the same logic. If we show that minus 1 times A is the additive inverse of A, then we will have that minus A is equal to this element. Now how to show that? First, let me give you this scratch. Like, what we want to obtain is A plus minus 1 times A is equal to 0. We should, if we have this, then we are done. But in order to have this, what we can have, like, how we can write this? We can write this as such. Here this is 1, so 1 plus minus 1a is equal to 0. This is also known fact because 0 times a is equal to 0, so we will arrive at this. In fact, we can now write this in a more neat way. It was the way to think, like how to arrive at this fact. First writing this, then trying to add like one here to make the distributive law and to arrive at what we desire from the known facts and axioms. Let's write this down. Since we know 1 plus minus 1 is equal to 0, we can multiply a to both sides, right? Multiply by a. Like here, it's worth mentioning that multiply on the right by a, since we don't know the commutativity yet. In a ring R plus cross, we have that R and plus R is the abelian group, but we don't know anything about the multiplication, so we cannot assume that multiplication is commutative, so we cannot write AB is equal to BA all the time. So that's why we can multiply on the right. Here we will have 1 plus minus 1 times I, or on the left, by the way, it doesn't matter. 0 times A. Now 0 times A is equal to 0, we already showed that, is equal to 0 by 1, it was, right? But from the distributivity, we also have that this distributes 1 times A plus minus 1 times A is equal to 0. I'm not writing distributivity here, it's clear. Now 1 times A is A, so A plus minus 1 times A is equal to 0. It's also by the axiom. We show that if there is an identity, then it should satisfy 1 times A times 1 is equal to A. Now once we have this, we are done, because let me write this. So minus 1 times A is the additive inverse of A, hence minus A is equal to minus 1 times A, and this is the end. Okay, this is the end of the whole proposition, the proof of the whole proposition. Let me make a quick recap of what we did to show you, like, if you don't have time to watch the video, you can just come here and look what we did, like it's written, and if you have some questions, you can go back to that to the part of the video and watch, or you watch the entire video, for which I'm thankful to you. Now, none of these identities are particularly difficult, and perhaps at first glance they may even seem too obvious to deserve a proof, but mathematics is built precisely from such elementary observations. Later, when we study ideals, quotient rings, homomorphisms, and many other constructions, we'll use these facts almost without noticing. So they become the part of the language of the subject. In a sense, they play the role of the letters in an alphabet. Individually they are simple, but together they allow us to write much more complicated mathematics stories. So, thank you for the watching, and I'll see you in the next video. Bye!